Okay guys, Mr. Papali here. Just wanted to go through a few different things related to the COVID-19 data. So first of all, welcome back. Second of all, we want to go through some ideas here. So what we've got is we've got some basic exponential plots here. So in this case, what we have here is x and y. Just to kind of refresh ourselves, this is y equals 2 to the power of x, exponential function with a base of 2. And when x is 0, 2 to the power of 0 is 1, 2 to the power of 1 is 2, and so on. We can see that this is doubling with each successive x increase. Over here, what we've done is we've given ourselves an initial value here. Okay, so this initial value equals 3, and so we start with 3. 2 to the power of 0 is 1, and 3 times 1 is 3. Okay, this is for those of you in grade 11 or 12 and you're dealing with transformations. We've got this vertical sort of stretch here, but it's also an initial value. What we've done here is we've given ourselves an initial value here equals 2, and rather than doubling, now we're increasing by a factor of 10. Right, now we're increasing by a factor of 10 for each x value. So we start with 2, right? 10 to the 0 is 1, 2 times 1 is 2, but then 10 to the 1 is 10, 2 times 10 is 20, and 200 and 2,000 and 20,000. We see there's some enormous growth patterns here. So we can generalize this equation. Okay, y equals a, which is our initial value, and we're going to call this rate. Okay, sometimes it's called b or whatever. Abstract, this is rate. So this is kind of like growth rate. If it's doubling, it's a 2. If it's growing by a factor of 10, it's a 10. If it's growing by a factor of 3, it's a 3, etc. So I'm going to give you a problem to think about here for a second, and that's this problem right here. So what we're going to do is we're going to say, okay, we've got at time 0 or x equals 0, we've got 3 items, whatever they are. And what we're going to do now is we're going to say, so it's similar to this question here. It's similar to this question. What we're saying now is we want it to take 2 days to double rather than 1 day. Right here, each 1 day is a double. Now it's going to take 2 days to double. I want you to try to come up with an equation or a table of values, depending which class you're in, whatever it is, that will help explain that. So what equation would model that situation? So pause the video and have a look at it. Okay, so what you should see here is that we start with 3, and it takes 2 days to double. Takes another 2 days to double, and another 2 days to double. So what we've got here now is we've got this this factor here, okay, and we might call this, in this case, a doubling time. Okay, this is an important idea. Okay, this doubling time, what this tells us here is that when x equals, say x equals 0, let's say x equals 2. When x equals 2, 2 divided by 2 is 1, so it's doubled once. When x equals 4, 4 divided by 2 is 2, so it's doubled twice. Okay, so this entire exponent area here is the value that 2 is to the exponent of. Okay, but this 1/2 here will slow down that process. Okay, the smaller this number is, the more time it takes to double. So we can generalize again. Okay, let's generalize again. And we're going to say now y equals a times 2, and sometimes we use this value k, and I'm going to use a t now. So t represents days, time, okay, and K is this, okay, in this case doubling time constant. And let's now take a look at some data. And before we do this, if we were to plot these ideas, okay, we'd be kind of a situation where our graph would look like this. Okay, this is a classic exponential graph. So let's take a look at some real life data, stuff I've got from the COVID-19. We can see the countries we've looked at here. Okay, let's run this chunk here. We'll see what we have. So this is the date. We started at February 24th, and here we are moving. We can kind of get a sense of the picture. So I want you to have a look here. I'll pause the video, you pause the video, and have a look at which countries are growing quickly and what that steepness means in terms of how quickly the virus is spreading in each country. So hopefully you've had a chance to observe some of these lines here. So we've obviously got some steeper slopes, some shallower slopes, things that have flattened out. So when we talk about flattening the curve, yes, there's been another visual, but there's another way to kind of see what we're looking at. So let's have a look at just sort of generalizing, because we're going to do something interesting here. So this is the general formula. You guys that are in younger grades, it's going to be a little bit awkward for you, but just kind of bear with me here. If we take the log, in this case I've got log of both sides here, we're going to end up with the log of y equals the log of a. And then remember, there's a rule that the log of a value times a value becomes a plus. And there's another rule whether if we have an exponent here, it actually becomes a coefficient. K log 10. Now log 10 is a special value. It equals 1. And then I've got a t here. So let's rewrite this. The log of y equals, and I'm going to kind of change the way this is organized. So log base 10 of 10 is 1. Okay, so we're going to say this is kt plus log a. And what we've got here is actually really interesting. If we take the log of one side, this kt, okay, and log a, these are coefficients of y equals mx plus b. Okay. Similarly, I can do a log base 2. Log base 2 of y equals log base 2 of a plus, and in this case, it's going to be, I'll simplify it, kt. Okay, so have a second to let that kind of marinate and dissect, and then we will show you a few plots. Consider what what is this? This is a line. Okay, so what this is telling us, okay, have a second, I'll pause the video, you pause the video, and have a think, what should an exponential graph look like if we do a log transformation on the y? Okay, let's consider that for a second. Okay, so what we've got here, actually, what I've done here, so whether you read the code or not, no big deal, but what we see here is I've changed the scale now to be a log 10 scale. Okay, here I've got a linear scale, 0, 20, 40, 60. Now let's run this chunk of code and see what kind of plot we end up with. Now we see some lines here. And let's kind of think back, what does the slope of that line mean? Okay, we already kind of should understand the y-intercept of that line. If we look at the y-intercept of that line, okay, it's the log, whatever base, in this case it's base 10, of what we started with, okay, at that date. But the slope of that line is this growth factor. And if we're talking about a log base 10, which this is, right, it's a log base 10, that slope of this line will tell us how long it takes to increase by a factor of 10. You can see the scale here, 10, 100, 1,000, 10,000, okay, by day. Okay, I'm going to continue on here, and we'll have a look here. This is another plot. This case, we've got now, rather than using dates, okay, what I've done is I've taken our base date where I thought we might be kind of at the top here, and I've said, okay, from February 23rd, that's going to be day 0. Okay, that's going to be day 0. What do we look like? And we can see some big time curves here. This one here is particularly alarming. Look how quickly it shot up. Okay, a change in that means that the doubling time, or in this case the factor of 10 time, has decreased. Okay, let's do one more. Again, now I've got days since. So I've done that so I can do a model on it, which is helpful. So if we think back, the closer this number is to 1, that means it doubles in 1 day. If this number is 0.5, it'll double in 2 days. Or this is a log 10 model, so it'll go to a factor of 10 in 2 days if it's a half. Okay? If it's 0.25, it'll be 4 days for a factor of 10. Okay? Now let's take a look at some log-based tool regressions. Okay, this is going to be the doubling time. I'm just going to go right to the end here, and we'll kind of see. Now, look at what we've got here. So this is a log-based 2 model. Okay, so these are now doubling times. Okay, so the basic country, so the one that's not in here, so I've got Iran, Italy, UK, South Korea. So I think this is Germany. Germany is our base model here. Okay, and from there, have a look at the numbers and discuss who's doing best, who's doing worst. Okay, so let's have a look at individual models now. The model is log-based 2, so this is now doubling time. Let's see how Canada is doing. We haven't looked at Canada yet. Let's see how's Canada doing for doubling time. Okay, this is about 0.25, so it's taking about 4 days, right? 0.25 is 1 over 4. It's taking about 4 days for Canada to double at its current pace. How is, let's see, Germany. How's Germany doing? Again, this is aggregates over time. Okay, linear model aggregates over time, so keep that in mind. So Germany, 0.4. Okay, so they're doing a little bit worse. They're doubling every 2.5 days, right? 2/5, and the reciprocal 2/5 is 5 over 2. That's 2.5 days. How about Italy? How's Italy been doing here? Let's have a look. 0.28. Okay, again, right around us. 0.25. How's the US doing? Let's have a look. Okay, so struggling a little bit, right, into that sort of 2.5, 3 day range. Anyways, guys, it's a little kind of primer to get you back into it. We've got lines, slopes. I haven't really spoke about y-intercepts. We've got logarithms. We've got exponents. Lots of different math to kind of get us back going. Your teacher will use it however they want. Maybe just a topic of discussion. Maybe it'll be more of a primer for the year. Anyways, thanks a lot for bearing with me. Appreciate it. This has been fun making this, and have a good day. It's good to see everyone.